Hello everybody, this is today's science video for Monday, May 18th. We are starting a new unit, as you guys could see from your packets, Light and Sound, Unit 14. You see on this, I have the colored version, it's a picture of fireworks, right? It says sound, and the big idea in this unit is that sound and light are forms of energy that are carried in waves. Usually when we think of waves, we think of water, right? But sound and light also travel in waves, a different type of wave, okay? On the bottom of the page, it says, I wonder why. I'm going to read that, okay? It says, when I watch fireworks from a distance, why do I see the fireworks exploding before I could hear them? Turn the pages to find out. Okay, so that's a question we're going to answer at some point in this unit, okay? So if you turn the page over to 646, at the top, it kind of tells you why you're learning what you're learning. I like to include this in the lessons. Also what the essential questions are, the big idea. So lesson 1, we're going to be focusing on what is sound, okay? That's lesson 1 right there, okay? I'm going to read the top. Here's why, okay? Just follow along with me. It says, sound and light waves are two forms of energy that your brain detects from its surroundings. The bright light from the fireworks travels faster than the sounds of the explosions. That's why sometimes you'll see a burst of distant fireworks before you hear the explosion. In this unit, you will explore the big idea, the essential questions, and the investigations on the inquiry flip chart. Okay, so we get to the essential question of lesson 1. What is sound? Okay, we know it's something we could hear, right? But what is it scientifically? So I'm on page 647. Okay, so it just says what the essential question is, what is sound? Engage your brain. It says, find the answer to the following question in this lesson, record it here. How does a drummer make music? Okay, we'll come back to that later, okay? In active reading, it says compare and contrast. In this lesson, you're going to read about how the characteristics of sound are alike and different from one another. Active readers stay focused on comparison and contrast when they ask themselves, how are these things alike and how are they different? Okay, so we're going to get started with the lesson. Okay, first page of the lesson is 648. Okay, it says waves of sound on the top. Okay, I'm going to read the top right here where it talks about waves of an ocean, okay? And I'm going to read right up here, so follow along. You may have seen water waves that look like this. Water waves move in an up and down motion, as shown here. No matter how a wave is shaped, it carries energy. So then it says, like I said, waves of sound. That's the main idea of this lesson. Some waves are long and flat. Other waves are tight and tall. But all waves move from place to place in a regular way. Okay. Water waves carry energy as they move, one after another across a lake. A wave is a disturbance that transmits energy. That's the definition of a wave, okay? So there are other kinds of waves that you can't see. Vibrations are the back and forth movement of an object. When you pluck a guitar string, the string vibrates, causing sound waves. The vibrating body of the guitar makes the sound louder. So that's why this is an acoustic guitar that this girl is playing. The reason acoustic guitars have this hole and they're hollow bodied is that it allows the sound to vibrate better, okay, and more, and make it louder. With an electric guitar, you don't have that. You just have all the wires that are inside the guitar, and there's some open body electric guitars, but you usually plug that into an amplifier, and that's what makes that loud. So for a classic guitar, you're just plucking the string, and then the sound waves travel inside the guitar because it's hollow, so it kind of echoes almost like when you get to a room that doesn't have a lot of things in it and it echoes. So it's almost like an echo of the guitar, okay? So the strings on the guitar are obviously the thing that vibrates, that starts the sound, okay? On page 649, at the top, it shows a bunch of different, what they look like circles, right? Different patterns of circles. The first one, they're really close together, and then they spread farther apart. The second one, they're far apart, and then they're compressed in the middle, and then they spread out again. And then in the last one, they start out far apart, and then they look like they got squeezed together at the end. Okay, so let's see what this is. It says, thinking of a spring toy can help you understand compression waves. So they're comparing it to, if you guys have ever played with a slinky, kind of looks like this, but it's connected. Okay. The coils in one area become bunched up or compressed. Then they stretch out and separate. In the number 2 and number 3 picture, these compressions and separations occur along the length of the spring as the wave moves away from its starting point. Okay, so this is compression, means something is close together. So this is starting out really close together, and then as sound travels, it will get farther apart. And then this is another type of compression wave where it's starting out and then it's getting bunched up, compressed somewhere, and then it's spreading out again. And then this is the opposite. It's spread out first, and then it's compressing at the end. Okay, so I'm going to read the main paragraph on this page, okay? It says, musical instruments aren't the only things that make sound. We know that. Striking the nail of the head of a nail with a hammer causes sound vibrations too. Many animals make sounds by moving a column of air up through the throat and mouth, just like us and like I'm doing right now. I'm talking and I'm creating sound waves, okay? Vibrations in my throat and then in my mouth. All sound vibrations travel in compression waves. As a compression wave moves, molecules of air and other matter are pushed together or compressed. So compression, the definition of compression is to push together. You'll sometimes see when you get packages, there's maybe bubble wrapping, and it might say compressed air on it. That just means that the air is pushed together, and that's how it forms those bubbles, okay, that we like to pop, and it's fun to, hear it pop and make all that noise. It's the same concept. Sound is compressed, and then as it moves out, it gets less compressed. It spreads apart, okay? So it says, as a compression wave moves, molecules of air and other matter are pushed together or compressed. Then the molecules spread apart. Sound energy moves away from its source as this bunching and spreading of molecules is repeated over and over. Your ears detect sound waves when the waves make part of your ears vibrate. Your brain interprets these vibrations as sound. So first, your ears detect the sound waves, okay? They're the ones that kind of like this receiver. They kind of receive the sound, but then it's up to your brain to interpret what the sound means, okay? When you're hearing me talk, it's not your ears that are giving meaning to the words I'm saying. It's your brain. So it travels in through your ears, and then your brain kind of translates everything and kind of explains to yourself what you're hearing. I know it's a little strange, it's complicated, but we receive these sound vibrations in our ears, and then our brain kind of tells us what we're hearing, okay? So if we hear a loud sound, our brain might think it's an explosion or a firework or something like that, okay? We didn't get into molecules, so I'm kind of going to backtrack here for a minute. Molecules are basically the basic building blocks of life. We're all made out of molecules. They're just like these invisible things that everything, living thing and non-thing is made up of, okay? So they're talking about sound molecules. It's just sound particles. If you look at this picture, they're just making it as if you could see it, because you really can't see molecules or particles, sound particles, right? We just hear it. So to break this down, sound starts out from a source. It starts out compressed. So when I'm projecting my voice, it starts when it's closest to me while I'm talking, it's compressed. And then as it travels through space, it gets spread out, okay? And then eventually, it dies out. My voice doesn't carry on and on and on. So yeah, it just, sound could be compressed by, a wall. Like say sound is traveling from one point to another and there's a wall, it's going to get compressed a little bit. You might hear sound through a wall, but that's kind of like what I would say. I think of the example of number 2. This is kind of like traveling, and then maybe it hits a wall. So like maybe you hear someone talking in the next door room, but it's gonna not be as loud as if you were right next to that person, right? So the sound is traveling, it's spread out, and then it, a wall structure stops it, okay? It kind of muffles it a little bit, and then it kind of spreads out again, okay? The first one, I kind of gave you the example with my voice. When it's starting from my throat, it's really compressed the sound, and then it moves out. And as the further it moves out, the less loud it gets. So if you almost think of a wave, they said like a real wave, like a ocean wave. Think of how the farther it moves out, the more flat it is. Okay, the more it flattens out and kind of doesn't become a wave anymore. So think of sound the same way, okay? It's like the farther the sound travels, the less energy it's going to give, okay? So that's kind of what sound is in a nutshell. It asks you to answer a question on page 649. The question is to tell how a compression wave and a water wave are alike and different. Okay, so they want to know how compression waves, which are basically sound waves, are like ocean waves or water waves, and how they're different. So the way I would answer this is they both fit the definition. If you go back to the beginning of our reading, it says water waves carry energy as they move, one after another across a lake. Okay, so they both carry energy as they move. Sound, like I said, that carries energy, just like a real visual wave, water wave carries, okay? So the first part of the answer is they carry energy as they move. And then the difference is water waves you could obviously see, and compression waves you can't see. Sound particles and those compression waves that travel throughout the air, that we call sound, you cannot see, right? So this is the answer, okay, if you want to copy it down. They both carry energy when they move. Oh, I'm sorry, as they move. It's backwards for me. So they both carry energy as they move. Water waves you can see, and compression waves you cannot see. You can't see. Okay. Okay, so that's it for today. When we talk in our individual sessions, we could talk a little bit more if you guys are confused or you have questions. But essentially, like I said, sound waves are just like very similar to ocean waves. You just can't see them, okay? The farther sound travels out, the less energy it gives off. It's the same thing with ocean waves. The farther it travels out from the source, from when it forms, the less energy it gives out, okay? So that's it for today, and thanks for watching, and we'll pick up with science on Wednesday, okay? Thanks.